NanoHub U, online instruction.
Hey everyone, welcome to lecture 310. So now we're going to talk about index-guided waveguides in MEEP. And so the reason we're doing this is because we had already talked about what are the basic components and classes of MEEP. But in order to actually get any results, we have to run the calculation. And so that means basically doing time stepping in our case. And so there are a few different run functions that are of interest. And here basically I've just briefly listed what the main options are. So run until basically means you tell it a certain number of time steps. It runs until the number of time steps is completed. Run sources basically says that based on the sources that you've input into the system, run until the longest running source has ended its time. Run sources plus just adds a certain amount of time. So it's kind of a combination of the first two. Stop when fields decayed is an interesting approach in which you basically would excite the system with a certain set of sources, but then you would wait until the fields have decayed by a certain fraction of the maximum value of the energy in the system. And so that actually is a fairly flexible and nice way to do a lot of calculations. And then there's this run k-point, which can also be useful if you're trying to calculate band structures akin to what we had in Unit 1, but through the finite difference time domain method instead. The advantage of doing that basically is that you could include materials that couldn't be included otherwise in the eigenmode solvers. And then when you're running these calculations, during certain steps, you can actually do other things that may be helpful. For example, you can output either the epsilon distribution of the dielectric materials, or you can output the electric or magnetic fields or the total power that's being output. And so those are just some examples. And so now when we go into the actual calculations, then of course we have to bring all those classes and features together into a cohesive framework. So here it's this is based on the tutorial for MEEP. It's showing that we have to start off by defining the geometry of the lattice. And so here we're basically in the first line just setting the lattice to be a certain size. And you notice that it's 16 by 8 by no size. So no size is basically a special command that tells you that this is a dimension that we don't want to compute, so we just leave it out. So that says basically it's a 2D problem instead of 3D. So that's why we have like the ability to get arbitrary geometry very easily. So then once we've defined that, then we create a single block, and that block is our waveguide. And it's centered right in the middle of the system at 0, 0. And it has infinite size in all directions but one. So it's finite in the y direction. And it's made out of a high dielectric. And then we define a source, which is basically on the edge of our system. Okay. And the reason that we know that's on the edge is that we said center is at 0 and the size in the x direction is 16. So that means it goes from -8 to +8, but we put it at -7. So that's close to -8. And then just beyond that -7, from -7 to -8, and then +7 to +8, then we put this perfectly matched layer, which is listed here. Then we set the resolution of the grid, which basically will also determine the max frequency that we can use to be 10. And then 10 is like usually considered reasonable choice for a lot of these problems. And then we run until, so that basically means run for 200 time steps and output the epsilon and the E field. And so the dielectric function from output epsilon looks like this, which is what we expected. And then when we look at the EZ fields, then we can also see the field propagation and pattern is alternating between positive and negative values, which is exactly what we had expected. In the next lecture, we'll talk in more detail about what happens when you start bending the waveguides.